Today we're diving into a paper titled Matryoshka Representation Learning, which explores a novel approach to creating flexible representations for machine learning tasks. What's the core problem this paper addresses?
The paper tackles the issue of fixed capacity representations in machine learning. Traditional representations are often designed with a single, fixed dimensionality, which can be inefficient for tasks with varying computational constraints. For example, a high-dimensional representation might be overkill for a simple task, while a low-dimensional one might not be sufficient for a complex task.
So the goal is to create representations that can adapt to different task complexities and resource limitations. How does Matryoshka Representation Learning, MRL, achieve this flexibility?
MRL introduces the concept of Matryoshka representations, which are essentially nested representations within a single high-dimensional vector. The idea is to learn representations of varying capacities within the same vector, allowing for different levels of information granularity.
Can you elaborate on how these nested representations are learned?
MRL minimally modifies existing representation learning pipelines. It introduces a set of nesting dimensions within the representation vector. These dimensions are chosen strategically, often with a logarithmic spacing, to capture information at different levels of detail. The model is then trained to optimize the task loss for each of these nested dimensions.
So instead of training separate models for different representation sizes, MRL learns a single model with multiple levels of information within the same vector. This sounds like it could be very efficient. What are the key benefits of using MRL?
The main benefit is the flexibility it provides for adaptive deployment. You can use the lower dimensional representations for tasks with limited computational resources or for tasks that don't require high accuracy. For more complex tasks, or when higher accuracy is needed, you can leverage the higher dimensional representations.
That's a very compelling advantage. Can you give us some specific examples of how MRL is applied in the paper?
The paper focuses on two key applications: large-scale classification and retrieval. For classification, MRL enables adaptive cascades where the model progressively uses higher dimensional representations as needed based on the confidence of the predictions. This can significantly reduce the average dimensionality required for a given accuracy level.
So instead of always using the full capacity representation, the model can dynamically adjust its complexity based on the input data. What about retrieval?
For retrieval, MRL allows for adaptive shortlisting and re-ranking. You can initially shortlist candidates using a low-dimensional representation and then re-rank them using a higher dimensional representation. This can lead to significant speedups in retrieval without sacrificing accuracy.
That's very interesting. So MRL essentially allows you to trade off accuracy for efficiency in a controlled way. Are there any limitations to MRL?
One limitation is that the choice of nesting dimensions and the relative importance of each dimension can be challenging to optimize. The paper explores some ablations on these parameters, but further research is needed to develop more systematic methods for optimizing these choices.
That makes sense. It's always a trade-off between flexibility and complexity.
Yeah.
What are some potential future directions for research in this area?
One promising direction is to explore the use of different loss functions for different levels of information granularity. For example, you could use a loss function that emphasizes recall for the lower dimensional representations, and a loss function that emphasizes robustness for the higher dimensional representations.
That's a good idea. It could allow for more fine-grained control over the trade-off between different aspects of the task. What other directions are worth exploring?
Another interesting direction is to investigate the use of learnable search data structures, such as differentiable KD trees, in conjunction with MRL. This could enable more efficient and data-driven adaptive retrieval.
That's a very interesting idea. It could potentially lead to more efficient and accurate retrieval systems. Are there any other potential applications of MRL beyond classification and retrieval?
Yes, MRL could be applied to a wide range of other tasks, such as few-shot learning, long-tail learning, and even analyzing the hardness of classification problems. The paper explores some initial results in these areas, but further research is needed to fully understand the potential of MRL for these tasks.
It seems like MRL has the potential to significantly impact the way we design and deploy machine learning models. Can you summarize the key contributions of this paper?
The paper introduces Matryoshka Representation Learning, a novel approach to learning flexible representations that can adapt to different task complexities and resource limitations. MRL enables adaptive classification and retrieval, leading to significant efficiency gains without sacrificing accuracy. The paper also explores the potential of MRL for other tasks, such as few-shot learning and long-tail learning.
This is a very promising approach. It seems like MRL could be a valuable tool for developing more efficient and adaptable machine learning systems. What are your overall thoughts on the paper?
The paper presents a well-motivated and well-executed approach to learning flexible representations. The results are compelling, and the paper provides a solid foundation for future research in this area. MRL has the potential to significantly impact the way we design and deploy machine learning models, particularly in resource-constrained environments.
Thank you for sharing your insights on this interesting paper. It's clear that MRL is a valuable contribution to the field of representation learning, and it will be exciting to see how this research develops in the future.